Our next guest is Muriel Medard, the NEC Professor of Software Science and Engineering at MIT. Professor Medard is an inventor of random linear network coding, or RLNC, a patented technology used in 5G and satellite communication systems. Her work has already been used by industry leaders like Cisco and Ericsson, and now she's bringing her expertise to the Web3 space by using RLNC in Optimum, an infrastructure for blockchain designed to eliminate a lot of the problems surrounding scalability bottlenecks and efficient storage. How will the technology of Web3 evolve, and ultimately, what does the future of global finance look like with faster, more efficient peer-to-peer systems? Professor Medard, welcome to the show.
Great to see you, David. Thank you so much for having me.
Professor, you are one of the, I want to call you inventors or project originators of something called the random linear network coding. It's interesting technology. Tell us what it is, how it's used by satellite communications. Tell us a little bit about your work leading up to this project before we talk about how it impacts Web3.
Yeah, thanks a lot. So I've been leading for the last 2 decades the Network Coding and Reliable Communications Group. It's part of the Research Lab for Electronics at MIT. And what network coding is at a high level is representing data, not just as straight up data, but as equations which are effectively equivalent to the original data, but actually have much more flexibility and allow for greater robustness, greater efficiency in transporting or storing data. So that has been really my life's work. And very early on, I became quite interested in doing this in a decentralized way. That's to say, not having a single entity that's orchestrating and creating all of these equations, but allowing a decentralized approach to creating these equations in a way that still maintains the integrity, robustness, and security of the data.
Okay, maybe describe to the layman watching how some of these technologies could be used and applied on an industrial scale today.
Absolutely. So suppose that you and I are chatting right now, David, and I'm trying to send you some data. Now, as we all know, data is just numbers. That's what makes it data rather than something else. And suppose that I have 2 different pieces of data. Let's call them X and Y to transmit to you. I could tell you X, I could tell you Y, but maybe there's a delay and you don't get X, you just get Y. That's not good enough, right? If I'm sending you a bank account and I only sent you the second half of the numbers of the bank account, that's not going to do it. You need both halves. So you might say, hey, look, Muriel, it looks like I'm missing X. I waited around for a while. You know, we have this discussion. I send it to you again. Then you reconstitute the XY pair. But, you know, that kind of takes a while and it's not very efficient. If I go, you know what, I really want to make sure that David gets both X and Y. And I really want to make sure that he gets X and Y in a timely fashion with high reliability. I could try to send X twice, but then what if Y gets lost? Then you have 2 copies of X and you're still missing Y. That doesn't help you. I could try to send X twice and Y twice, but that has used a lot of resources. You sent 4 numbers when you really just need to send 2 numbers, and you're pretty sure that one of them will get lost. So that's kind of wasteful. Instead, what I could do is I could send X, Y, and then send you just X plus Y. So let's see what happens. If X gets lost, like in our first example, you got Y and X plus Y, that's enough to recover X. You just subtract Y from X plus Y. If Y gets lost, you get X and X plus Y. That's good enough to recover both numbers. And of course, if X plus Y gets lost, No harm, no foul. You already had the X and the Y. So in that case, if you will, the extra data that was sent matches the lack of reliability of the channel, those losses, as we usually call them, and you're not wasteful in what you've transmitted, but also that means that we don't have to engage in a whole conversation about what you got, what you didn't get, when you got it, when you didn't get it. And it really speeds up and smooths significantly the communication that we have between the two of us.
Oh, well, RLNC has already been deployed in 5G and satellite systems. Can you highlight some of the key improvements in those infrastructures that the technology has already made?
So it has been deployed in software-defined wide area networks currently, and it's also deployed in systems that have very challenged environments, such as underwater systems. So that's the kind of system which can really benefit when you think of these losses. Now, why are we doing this now in Web3? The reason we're doing this in blockchain and Web3 is the added complication is the complication of scalability when you have a decentralized system. And so the challenges there are perfect for RLNC.
Well, one of the other challenges for blockchain tech is the bandwidth and storage bottleneck problem that a lot of existing blockchains and layer ones have. How does your technology solve those issues?
Yeah, that's a great question. Let me take one example, which actually connects to our first offering, Optimum P2P, which we've nicknamed Mom P2P.
Okay.
So if you think of systems like, for instance, Ethereum, but there are some other systems out there. It's a decentralized system. You have what's called propagation. You need to have validators in the system exchange information. And that can take a long time. Think of it as taking multiple seconds, which is very different from the kinds of latencies we're used, for instance, in Web 2, where, if you told me that any sort of service in Web 2 is going to take seconds, I would say, I don't think people are going to want to use it. That's way too slow. So what is one of the reasons it takes so long? Well, it's uncoordinated, it's decentralized. So you have different nodes in the network trying to exchange information with each other. And the way they exchange that information with each other is they do what's called gossiping. And gossiping is exactly what it sounds like. I find something out, I tell some of my neighbors, and then there's all kinds of exchanges that take place. So that kind of gossip can become actually really inefficient. Why? Well, you want to have every node communicate with enough nodes so that there's actual exchange of information. Like if you have a network that relies on gossip to disseminate, but nobody talks to anybody, nothing's going to disseminate. On the other hand, if you have too much communication, then people are wasting a lot of resources repeating information that was already known. So it's like, you've heard the same piece of information from 4 different neighbors. That was a real waste of time. That time that you spent, you could have spent on new information rather than old information. So that's what current state of the art is struggling with. If you look now at using equations, a little bit like we just described, the x plus y, but just like more complicated equations, but similar concept. Now what happens is rather than repeating the same thing to you, rather than telling you x, say twice, 3, 4 times, I'm actually each time telling you a new equation. And the way we construct our equations is such that it's highly likely that the equations that you get are telling you stuff that you didn't know before. So the example we had 2 unknowns, x and y, 2 unknowns, 2 equations, that's all it takes. Suppose that I told you now I have 10 unknowns. I just need 10 equations. And as long as those equations are sufficiently different, I can actually reconstruct the original data. So then I don't have any wasted transmissions. I'm making optimum use, hence our name. I'm making optimum use of all the transmissions of information, and everything that's been told to me is something that is actually useful for reconstructing the data.
Another common problem is that during periods of high network congestion, a lot of crypto users experience high fees, slow confirmation times. How do you plan to change, or how could this tech change that scenario?
That's a really, really good point. So what happens in any network, whether it be a network that's exchanging data or a network that's transporting cars, is that there's a very nonlinear relationship between the load and the delay. So let's think of, for instance, being on a road. We all know what happens. Either traffic is light, there's no delay, or you're in a traffic jam. There's not a lot of times where you feel that, hey, there's a lot of traffic on the road, but this is great. I'm not getting backed up. There's no delays. Amazing. Things are going great, even though it's not very, yeah, even though there's a lot of traffic. And there's reasons for that. And it's the same thing that happens when people are doing transactions. If there's a lot of demand, you get backed up. And once you start getting backed up, your system gets really sluggish and you have to back a lot away from that level of usage of the system. So what does Optimum do? What Optimum does is that it completely changes those dynamics so that the point at which you get backed up now happens much, much later. So let's give the example going back to the data propagation that we were talking about. Remember,
Sure.
if I don't code, I'm going to get, say, 4 copies of X, which means that it's like you gave me a highway with 4 lanes, but I'm only using 1 lane because it's the same car traveling, just picking up all 4 lanes. How is that useful? So I've really wasted my lanes. With coding, now you get to use your 4 lanes fully because it's 4 different equations. So it's means that, rather than having a 4-lane system that's working like a 1-lane system, you actually get your 4 lanes. And therefore, the point at which you're going to encounter a traffic jam massively changes.
Okay. So in the context of crypto, how is it that Optimum is going to fix the problem of perhaps more decentralization being slower? I think that's one of the concerns from a lot of crypto users, that as a blockchain becomes more decentralized, you get slower performance.
That's a really good point. So that trade-off between speed and decentralization is a trade-off that happens when you don't code. That's why people have actually experienced it. And basically, if you code, that apparent trade-off goes away. So it's not an inherent property. It's actually a experience that comes out of bad algorithms. So what happens is, if you're going to have a lot of repeats, you go, hey, I need somebody to try to control what's going on, tell people not to send too many repeats, but that doesn't scale. Why does it not scale? Because, if you're going to try to have a central controller, you need to get fresh information to that controller so that that controller can actually take action. And if your network grows, that amount of information is going to grow, and the delay to get that information will also grow. And eventually the whole system is just going to collapse under its own weight. So the decentralization and the speed is actually a false trade-off. It's, if you will, a simple side effect of inefficient algorithms.
Are you aware of the so-called Bitcoin or blockchain trilemma,
Yes.
where it's argued that you can't have all three: scalability, security, and decentralization? Some projects have claimed to achieve that. Where do you stand on this debate?
Yeah. Thank you for bringing that up. I think it's a really, really good question. It's a core question. So let me start with the fact that the trilemma is very clear from the get-go, that it's not a theorem, it's not a lemma. It's, if you will, a meta remark, and I think it was definitely a very useful meta remark. If you think really on the mathematical side, there is something called the cap theorem, which was actually established by one of my colleagues and friends, and actually an advisor to our project, who had the NEC chair in software science and engineering before I held it. So I sort of inherited from her, Nancy Lynch. Some of our listeners might know her. She's, a giant in the field. And I think that the trilemma was maybe a little bit of a reinterpretation of that theorem, but that theorem says very specific things under very, very specific conditions. In general, that trilemma is, I think, generally misinterpreted, has been misinterpreted. And actually, we have a recent piece on that, along with Dr. Conwar, our CTO, Dr. Nicolau, one of our Optimum researchers, basically showing that the trilemma, such as it is commonly understood, does not hold, and explaining why RLNC changes that trilemma framework.
Okay, well, with that in mind, let's move on to talk about Ethereum specifically. Let's talk about how Optimum is going to improve Ethereum. But before we do that, let's just review the last decade of Ethereum's performance. How would you evaluate how Ethereum has evolved from its genesis to where it is now, and what improvements could be made?
Yeah, I mean, I think by any measures, it has been an amazing project. The effect it has had, the penetration it has had, the variety of applications it has allowed. It's really impressive, and there's I don't think there's any other way to describe it. Now, I think if you go to sort of its general philosophy, if you think of it as roughly that an EVM matches to an operating system, let's think a little bit of what a computer is. There's a model for what a computer is. It's actually a question that people asked right after World War II. There had been all the big strides in computing that came out of, for instance, the Enigma machine and all of those, legendary progresses in computation. And von Neumann put forth a model for a computer which actually has quite stood the test of time. And the von Neumann model is the following. So the computer has a compute part, which has what they call the controller, which we would recognize probably as kind of the operating system. It has the arithmetic logic unit, what we would probably think of kind of like your CPU. It has a bus, and it has memory. And a lot of the work has gone, and of course it has to have an input and an output. And a lot of the work has gone around that compute part, and it's been amazing work. The bus and the memory don't look as recognizable at all. As, if you took, say, a computer architecture class in college, or even if you just decided to build a computer, you would say, wow, you know, for instance, using gossip for propagation, that's kind of a strange way to mimic a bus in a computer. So I think that Ethereum has done amazing things, but it's sort of starting to hit a bit of a wall on the part that I would say is propagation and memory versus the computation part.
All
And
right.
really,
And
that's where Optimum kicks in. That's how we're helping out.
you've said, I think, offline to me that validator coordination will be one of the big next frontiers for you for improvement. So maybe explain how Optimum P2P and RLNC can improve coordination on that front and potentially reduce latency.
Absolutely. And actually, we are right now in testnet and actually moving to hoodie testnet with a lot of validators. You can see an entire list on our website. I would say the majority of the very large validator projects we're working with. By the way, it's been a fantastic experience, and they've been extremely cooperative and collaborative. So what we do is we start with speeding up what's called the consensus layer, which of course is a core part of any blockchain, and Ethereum is no exception. And what we see is an improvement of an order of about a factor of 6 in the delay. So if you think of any system, improving latency by about 6x in any portion of that, of any portion of a system, particularly one where it's taking seconds normally, that's a massive improvement. What that means is, going back to what you were asking before about gas fees, that allows people to reduce gas fees, have faster finality. It allows validators to improve their APY. It basically removes artificial inefficiencies in the system.
So once these efficiencies are realized, Professor, what practical applications do you see being built on top of Ethereum that maybe could not exist today? And just stretching beyond Ethereum, once we achieve more optimal performance, pun intended, overall across blockchains, how do we see the landscape changing in terms of actual applications built on layer ones?
Yeah, that's a great question. And let me start by saying that, as you mentioned, our approach is not Ethereum specific.
Yes.
We're starting with Ethereum because it's a good place to start. It's a great chain. And our permissionless approach is able to manage that well. Our next step is actually to go to Solana, which uses some coding, but uses a very old-fashioned, very inefficient code called Reed Solomon, and which dates back to the 60s, 50s. So certainly we're looking to improve any chain, and we're looking to scale any chain.
Absolutely.
So I think that there are multiple. One can never always predict how giving a more powerful engine is going to allow new applications. So it's always a little bit difficult to guess. But certainly having a system which is going to allow for lower gas fees means that, and also enable people to have much faster finality. It means that certain applications, which right now are just not that attractive because they're too expensive or too slow, could actually become very feasible and very attractive. I'd like to add one aspect, though, which is not so much around the applications, but one of the things that Optimum allows. If you look currently at blockchain, blockchain is really very imbued in a culture of community. And there's sort of a couple of different ways in which members of the community can get involved, very roughly. One is as users of the technology, maybe, they trade in crypto, they follow, etc. Maybe that's, basically where it stops. Or they can contribute in terms of building software or being part of the infrastructure generally as validators. Being a validator is, it's a big commitment, generally requires a fair amount of upfront investment in terms of the machines, and then a lot of operational investment in terms of uptime, so that, for instance, you don't get slashed because your validator went down, etc. And those are sort of the approaches, and of course, some people do more than one. What we allow is we allow something that we call a flex node, which means that, let's go back to our equations. I can be a machine, I can run a machine that just propagates equations. It's not doing the heavy lifting of validation, is just a cog in a decentralized machine where I'm helping my neighbors, I'm helping my community with getting faster equations, and I get rewarded for it. So that aspect means also that we're looking at a much more decentralized infrastructure of flex nodes, where flex nodes can be small nodes, it can be large nodes, and they can be from small contributors or, of course, larger contributors. So that's really core to what we're looking to do.
So you mentioned that you're moving on to Solana next. Can you tell us about some of the major milestones that Optimum has already achieved so far? I believe you raised close to $11 million so far. You've launched a testnet with major validators, like you've mentioned previously. What's next besides moving on to Solana?
Absolutely. So as you mentioned, we have raised our seed round. We actually raised just under 12. We were looking for 10, but we were so heavily oversubscribed that we ended up trying to make sure that we could accommodate as many of the fantastic partners as were willing to join, even though we had to, as I said, we were very, very heavily subscribed. So we have our amazing testnet. I mentioned, the multiples, typically 6x. I don't think I've seen under 4x right now, but we've seen up to 9x improvements in latency. I mentioned that we have onboarded very significant number of validators who together represent a very large percentage of the Ethereum traffic. And what we're going to be doing next is, of course, working towards mainnet. We're also starting our network hackathons. The first one will be at MIT just next month, just in a couple of weeks, for people to basically play and see how you can bring up a flex node, the flex nodes that I just described. So bringing together a community of people who can operate and see the gains that they can get from operating a flex node. And then in the following year, we're looking for, so next year, we're looking for our Solana permissionless approach. Now, what comes longer term, and we've already started working on this, is moving not just to propagation where we're now, but the entire memory layer. Remember, I was talking about von Neumann, the bus, the memory. And if you think of your computer, you've got a bus, you have read-only memory, and you have read-write memory, what we call RAM, random access memory. The read-only memory is the ROM. So we are bringing, thanks to coding, DROM and DRAM, so a read-write random access memory. So that's our long-term roadmap, and that's a vision.
Okay. Do you have any advice for builders watching this program right now for how to develop a project or design a system for long-term resilience and also to optimize efficiency?
Yeah, that's a really good question. It's a very complicated question because there's so
Yeah.
many aspects to it.
I know you
I
kind of teach a course on this, but maybe summarize it for 2 minutes or less.
yeah. So I think that one of the things that to me is striking, going back to this computer analogy, and one shouldn't overwork analogies, but is the following. If you find that things are being done in a way that's different from what you would want to do in a computer architecture, it's worth taking a break and asking why, right? There has to be a good reason. Was this just because people had to pull something together quickly and that's kind of the best they could do under the circumstances? Is it because there's a really fundamental reason for doing it that way? I think it's really important. And, and this is this going to scale? Is this going to break? Are you building on sand? Are you building on something that's very, that's very robust? I mean, you were talking particularly about developers. When we think about programming, certainly, when people learn to program, they generally learn to program in a way which is fairly independent of the machine they're on. Sure, your program will work more slowly, less efficiently or whatever if you have a slow computer or a fast computer. But your basic programming, until you get into pretty complicated stuff, it's pretty much machine independent, right? I mean,
Yeah.
imagine if you were like, I don't know, learning Python and having to go, oh, darn, I have to check what kind of bus I have, what my CPU is. You think this is really not very modular. So if that's not what's happening right now, it's probably a kludge. So I think that in terms of robustness, trying to develop for the long term in a way that's going to stand the test of time means really going back to principles.
I'm curious how you would rate Satoshi's attempt to build a blockchain. I'm talking about Bitcoin. Reviewing the original white paper, Bitcoin was meant to be a peer-to-peer system. How would you rate or assess Bitcoin's peer-to-peer effectiveness? How would you rate its usefulness as a peer-to-peer system, and ultimately its other characteristics that we talked about, such as scalability, security, and decentralization?
So again, it's been absolutely remarkable, right? I mean, what it has achieved, its longevity, and so on. I think that the question there to me is a little bit more what it does. Let's go back to an operating system.
Yes.
When we talk about operating systems, we usually mean an operating system where I can program pretty much anything we want. I was talking about things like the Enigma machine, the name Turing comes to mind. And, then you're talking about something that's Turing complete, or pretty much I can program it to do whatever I want. Okay, maybe not at the speed I want and so on, but I can get it to do whatever I want. Compare that, for instance, with the operating system on my thermostat. I have a thermostat over there. It's not built to do everything, right? I mean, I don't know exactly what operating system it has, but basically what it's supposed to do is, bring the temperature up, bring the temperature down. That's kind of what it's supposed to do. And it does it really well, right? Would I want to program an arbitrary application on my thermostat? Probably not. So,
Yes.
so judging it as a thermostat, it's fantastic. It's a great
So we
thermostat.
shouldn't be judging Bitcoin based on Ethereum's properties. We should be judging Bitcoin based on what it does well. So what does it do very well?
It's an amazing distributed ledger, right? A decentralized ledger. It's an amazing ledger. So that's great. It's managed to do that remarkably. But from then to go, okay, I want to program this to run some arbitrary application. It's a little bit unfair that that's not, you know,
Some people
if
have
it does
attempted
that, then
that.
yeah,
There is this
yeah.
question as to whether or not people should be building layer twos to run, in your words, arbitrary applications on the Bitcoin layer one, versus just building a new project or a new chain altogether. Um, those are two extremes. What would you advocate for?
That's a really good question. My general view is that it really becomes a question of the particular trade-offs that people have, right? If they
Hmm.
go, well, you know, maybe I'm not so interested in speed, and I really have a strong reason, whatever it may be, to try to use this as a ledger, and that's really what I'm trying to get out of. Hey, why not? But I think one has to be realistic about what something was built for. And, and as long as one does that and one is well aware of the pluses and minuses, that's fine. It's just a question of being lucid, I believe.
Looking ahead 5 to 10 years, how could Optimum and broadly RLNC reshape global finance networks, settle trades faster, and even collaborate with data heavy industries like AI to train models in the global finance sphere?
That's a fantastic question, David. We're building really what the decentralized memory layer. And going back to programming on a computer, what we want to do is to take optimum advantage of the available resources. That means whatever transmission resources there are, whatever memory that is, we want to provide a fully decentralized experience, a fully decentralized approach so that the experience is the same as if you were on a single computer. So people should be able to program basically not having to worry about, where's the data? How am I going to get access to it? And do that in a way which is transparent and as fast and as reliably as physically possible given the current given whatever the resources are that are available at that time, and do this in a decentralized way where flex nodes all over the world are helping each other out, are allowing people to get the benefit of Optimum, reap their own benefits, and help each other out without the need for centralization.
Well, I appreciate your time, and I feel bad that I am not smart enough to have taken your course at MIT. So I am.
It's not too late, David.
I think it's kind of too late for me, but I enjoy speaking with you
Never,
nonetheless.
never.
I'm wondering. I'm just curious. Is your course on the online MIT course catalog? Is that?
So, if you're interested in network
Yeah.
coding, random network coding, I just published a book with some collaborators. It's appealingly named Network Coding for Engineers. So, if there's engineers out there who want to read up on it, I recommend that they get the book. And I don't assume we don't assume any knowledge of math behind
Yeah.
behind the coding. It has Python examples, and so yeah, if people are interested in just
Hmm.
playing with the tech, by all means, we start from scratch and we take it very far in that book.
And where else can people learn about your work and what you're currently working on in the meantime?
Absolutely. Thanks for asking. Our website, getoptimum.xyz, has a lot of papers, a lot of resources, and we keep it very much up to date. Also, if people want to participate in our hackathons, I mentioned a first in-person hackathon next month. The following month, we're going to have one in person in Europe. And then we'll be doing online hackathons throughout the world. so that people can actually interact with the Optimum system and really in a hands-on fashion. Again, this is towards people being able to spin up their own flex nodes and become an active participant in the Optimum network. So if people are interested in saying, hey, I want to play with it, please stay tuned. We have a very large community on Discord where we have, and of course we're on X where we advertise those different activities. So if you want to read a book, and please read our book, read the papers that are on our website, get engaged in the community, participate in the hackathons. We really want to pull as many people as are interested into our project.
Okay, excellent. Well, I appreciate it once again. This was very educational, even though a lot of it went over my head. But we'll put the links down below to your work so people can study more and learn more about what you're currently working on. Thank you very much, Professor Medard. We'll speak again soon. Take care.
Thank you so much for the opportunity, David.
Thank you for watching. Don't forget to like and subscribe.